Hello, everyone. Welcome to the Hot Water Forum. And today you're attending a webcast on demand response, connected protocols and controls. I'm Jeff Wicks with NEA and the Northwest Energy Efficiency Alliance. I'll be moderating the session, and we'll start out the webcast with a few housekeeping announcements and then quickly move into our presentations. First and foremost, we want to thank all of our sponsors at ACEEE and all the ally members who support the Hot Water Forum, both now, in the future, and in the past. So please use the chat box on the right side of your screen to ask questions. I'll be collecting those throughout the session. We will not have those during the session. They will not be interactive. That will be part of the Zoom section afterwards, which is going to be for 20 minutes afterwards. The Zoom link will be posted in that chat area, so please pull that out when we're ready to move to the Zoom area. Be sure to check on the left side of the apps for all the different elements that the Hot Water Forum offers, and visit sponsor pages, engage with other people, and there is a chance to win a free registration to the 2023 Hot Water Forum, which will be this year in Mission Hills, California, or this following year in Mission Hills, California. All presentations will be available for an on-demand viewing to registered attendees within a few days. So if you find something very informative you want to go back to, please do that. Or if you're currently missing one, there are 2 other sessions going on simultaneously. So without wasting any more time, I'd like to get into the presentations because there's some great information here. The first one will be Don Shirey, and he'll be talking about how the findings and evaluation of Energy Star test method in validating demand response for connected residential water heaters. After that, we're going to have Mike Bromley with PNNL, water heater control method, demand reduction, and energy impacts of interactive homes. And then on cleanup, we'll have Tristan DeFonderville and Don Delchinos talking about Ecoport and connected appliances, how to test, qualify, list, and advertise your status. So let's get into the first presenter, Don Shirey. Don is a senior project manager at the Electric Power Research Institute. I think they're going by a different name, and Don, you might be able to correct us on that. He works at EPRI's Customer Technology Program, evaluating a range of end-use programs for residential and commercial and industrial buildings. Don manages research focusing on technology applications for energy efficiency, electrification, demand response, and grid flexibility. Don and his team evaluate space conditioning, heat pumps, heat pump water heaters, refrigeration equipment, dehumidification systems, and other technologies through computer analysis, laboratory testing under controlled conditions, and field deployments to monitor system performance and collect customer feedback. Don, take it away. Thank you so much.
Okay, Jeff, can you hear me okay?
You've got good audio.
Okay. Thanks, everyone, for joining today. Really appreciate your time. As Jeff said, I'm going to be presenting some results, some findings where we evaluated the Energy Star test method to validate DR for connected residential water heaters. Okay, just a little bit about EPRI real quick. You may not know about us. We're a nonprofit research and development organization founded about 50 years ago, serving for the public benefit, do lots of analysis, testing, thought leadership related to energy efficiency, do a lot of work with electric utility the electric utilities and other stakeholders, as well as government agencies like the Department of Energy and the California Energy Commission. So we have a collaborative model. We try to bring together lots of folks to work on problems. And anyway, that's EPRI in a nutshell. So a little bit about the project today. So I'm gonna, we conducted the lab evaluation of the test method in our lab. We applied the test method to a heat pump water heater that was on the market last year. Before it was actually manufactured, before the Energy Star test method was officially published. And we evaluated it and provide feedback on the new DR test procedures. So if you look at the DR test method, it has 8 sections: an overview, applicability, definitions at the beginning. It defines the test setup, the water heater preparation, And then the demand response test. There's an initialization test, user interface check, consumer override, loss of connectivity tests, demand response, requests and responses to a load shift and an emergency curtailment and a grid emergency test. And it checks for DR information and messaging coming back. There's some calculations to be performed, and there are references in section 8. So it was released last April 2021, and was effective this past January. So I'm going to focus here on the section 6 and then the subgroups override, loss of connectivity, and demand response. That's what I'm going to focus on presenting today. So the test setup, so we installed a 40-gallon heat pump water heater in our psychrometric chamber per sections 4 and 5 of the test method. And it did require a mixing valve. So this is something a little bit different that is required for this testing. We used EPRI's own CTA 2045 simulator, which is an AC form factor shown in the figure on the right. And then we actually run computer software on a laptop that communicates with this CTA 2045 device and sending the signals properly to the heat pump water heater. So customer override. So the test procedure states that the override shall be limited to a duration up to 72 hours. Now, the interesting thing is there's really no verification step in the procedure for this. It just says it shall do that. For the heat pump water heater we tested, it opted, the consumer override lasted 24 hours. So instead of the 72, it was 24, but the requirement was up to 72. So everything was fine with respect to the procedure. And again, I think there's a lot of discussion in the industry about what that should be. You know, 3 days, having it override and having it last for 3 days seems quite long. From an electric utility perspective, they normally run demand response requests, could be daily, could be Wednesday and then Thursday, and then if it's still hot, again on Friday. So having a 72-hour opt-out period is pretty long, and I would recommend it be 24, which is what the manufacturer of this product did. So there was loss of connectivity as well. So what it says is 15 minutes without connection during the DR event, but there's different categories. So if the loss of connectivity during the DR event with a set duration or end time, then the product can complete the DR event and return to normal operation set by the customer. So that's if you have a set duration and end time. If you don't have a set duration and end time, basically resume normal operation within half an hour. And then lastly, if the heat pump water heater is capable of storing and operating with time of use schedule, the unit can operate on the schedule during a loss of connectivity event. So since that TOU schedule is imported to the water heater itself, it can basically continue to follow that even if there's a loss of connectivity, because that schedule is stored locally. So what we found was a little bit of ambiguity regarding remove connectivity. So, you know, it's written up generically, so it allows for multiple connectivity pathways. But the question is it a loss of communication by lost internet connection, or did somebody pull out the CTA 2045 module from the water heater, or did it get loose and fall out? So, you know, the question is, you know, what are we testing for? We could test for both, but right now they're pretty much testing for it as if it were loss of internet connection. But so the method for checking the loss of connectivity during a DR event without end time is inconsistent. So if you look, it says duration equal maximum. So the red outline on the left-hand side of the screen says duration equal maximum. But in CTA 2045 lingo, maximum is really 36 hours. So it has an end time, it's just a long way away. So if you put duration equals 0, then it would accomplish without a set duration or end time, because 0 really means infinity, maximum really is 36 hours. So that's one thing. There needs to be a reconciliation of the text that's describing this step and then how we want to set the duration. There's also a typo on the step 12 in the left-hand graph, circled in red. After you send it a DR signal, it shouldn't say idle normal or run normal. It really should say running curtailed grid or idle grid. So that's just a typo, easy change in the procedure. So this is a list of the DR operational modes and responses. So the first column talks about the operational mode, general curtailment, and then the response is all the way on the right-hand side, first row. Avoid using energy that the device would otherwise have used under normal operating conditions. We allow the stored thermal energy to reduce moderately. So that's a moderate reduction, so that's subject to interpretation by the water heater manufacturer. For heat pump water heaters with the resistive element, the water heater will not use the electric elements during and immediately after the event, unless user needs cannot be met. So basically, you can reduce the energy consumption, maybe lower the set point or something like that. But if you have electric resistance, you really don't want those to come on at all during or immediately after the event. The next operational mode is emergency curtailment, which is basically the same as general curtailment, but you can do it to an even deeper thermal storage level within the tank. So maybe one example might be to reduce the set point even further than you do for general curtailment. And again, for heat pump water heaters with resistive elements, the request will result in heat pump only operation during the request period. And third is grid emergency, where you basically turn off the water heater until the end of the DR event. There is a load up function, fourth from the top. And basically here you are trying to add additional energy into the tank for use later. So normally you might use a load up and then follow it with a general curtailment. So you charge up the water heater a little bit more than normal, and then you go into a curtailment mode where you can extend or reduce power consumption for a longer period of time. There's a basic load up and an advanced load up. Basic load up basically means you turn on the water heater and let it come up all the way up to set point. So there's no droop in the thermostat. The whole tank is fully at the thermostat set point. And for advanced, basically, you can go above the water heater's normal set point. And of course, that's why the mixing valve would be required. So, you know, one example might be your standard temperature in the tank is 120, but you may want to do an advanced load up to, I don't know, let's say 135 degrees Fahrenheit. And then you'd use this command, and then normally you'd follow it up with a general curtailment to go low on energy consumption for an extended period. And the last function at the very bottom is return to normal. Let's see how I'm doing on time. Okay, so anyway, we did the load shift test, and the results are shown here on the right-hand side of the screen. Load up followed by general curtailment using the first 3 water draws from the UEF test procedure. So the DOE has the UEF test procedure defined, and this one just uses the first 3 of those, first 3 water draws there. So for minimum load shifts, they talk about either half a kilowatt hour or more via a combination of basic load up and general curtailment, or advanced load shift, 1 kilowatt hour or more with a combination of advanced load up and then followed by general curtailment. So let's see, if you look at the table in the middle, again, this water heater was manufactured before this standard was even finalized. So we didn't expect it to meet the requirement. We were more just testing the procedure itself. But load shift, they define it as the baseline energy consumption, which is the pattern of energy shown on the upper right. The orange is the power, and the blue line is the water draw out of the tank, the cumulative water draw. And then the lower right is where we did a load up. Then we had a 4-hour curtailment, and then we're showing here where the water heater heats up after the DR event. So for this particular water heater, it was about 900 watt hours of energy normally. The general curtailment only used 670, and the load up was 181. So it happens that the load shift of this is 405 watt hours instead of 500. Again, we didn't expect this unit to meet the requirement because it was before this was all finalized. One thing interesting to note, though, is if you look at the total time required for the test. So there's an hour to normalize the water heater, a 4-hour baseline test, then a 1-hour normalization, 1-hour load up, 4-hour shed, 1-hour recovery. So you're talking at least 12 hours of test. And for the load up event, if you don't pull out the water just right, you may have to wait another hour. So it's on the order of 12 to 13 hours to complete this load shift test. This graph is similar to the other. There's power is the orange shaded area, and the blue line is the cumulative water draw. And so we started out with an emergency curtailment where the unit seemed to reduce the set point significantly. The electric elements did not come on. And so it definitely met the requirement of no resistance element operation. In grid emergency, you can see with the red arrow there was no consumption. So it did exactly as it was told. Don't do any consumption for that period of time. The whole test took about an hour for this one. So it wasn't an extensive evaluation as compared to the load shift test, but it did prove out the functionality. Okay, so recommendations and conclusions. So for the consumer override, again, I think this has been something that's been around for a while. Changing space conditioning equipment normally changes the set point temperature as the method to trigger override, customer override. In the absence of a dedicated override button. So this particular device used a different keystroke to invoke consumer override. So the suggestion would be to either have a dedicated override button that's easy for the consumer to see, or maybe change the set point temperature so it aligns with other devices in the house that are using customer override by that temperature change method. I talked about it earlier. I would recommend reducing the maximum override duration from 72 to 24 hours. In terms of loss of connectivity, we really need to distinguish between the two cases. Again, whether you're losing internet connection or if the plug-in module actually comes out or falls off the device. We need to reconcile the inconsistencies that I noted earlier regarding loss of connectivity during a DR event without an end time, and we need to correct that one typo on step 12. Load shift, we might want to consider reducing the test duration. Right now it's pretty long, but maybe we can reduce the DR period from 4 to 3 hours, both in the baseline and in the actual DR load shift portion. So that would shorten it as well. It does require custom actions at certain steps. So right now, it would be very hard to fully automate the test as written. Straightforward, but there's some things where you have to wait for certain things to happen and certain temperatures, and it would take quite a bit of time to do that, to automate that. One thing, emergency curtailment, for alignment with AHRI 1380, which is DR for variable capacity air conditioning, I just recommend that we change emergency curtailment to critical curtailment. Then both standards are in alignment. There's a general curtailment, critical curtailment, and grid emergency. And those same levels would be defined both for space conditioning and water heating. And like I said, it's about 13 to 14 hours to fully complete the testing. It's it's the first prescriptive step-by-step DR test method for a residential product. So that's very important to have something that people can begin following and being uniform with their testing of DR. And basically, it does confirm product performance for all DR operational modes, and it successfully quantifies the load shift potential that the utility could use for demand shifting during congested grid periods. So I show the full report down here at the bottom, but that is it for today. Jeff, back to you.
Great, Don. Thank you very much. This is quite insightful, a dynamic place in the water heating world. And I would take this opportunity to mention that AHRI is also working on a water heating connectivity standard as well, and that's the 1430. And there is alignment in a lot of places. And in fact, Abby Dakin with Energy Star is participating actively in that standard. So great evaluation, and good to see that we're getting some good alignment on load shifting capability. Thank you. Nice job. So our next speaker is going to be Michael Bromley with PNNL Labs, and the title of his presentation is going to be Water Heating Control Methods, Demand Reduction, Energy Impacts in the Grid Interactive Homes. So Mike works at PNNL for over 30 years of academic and research experience related to energy technologies and policy, focusing on the last 22 years while at PNNL Labs and developing technologies improving building energy efficiency. At PNNL, Dr. Bromley has also served in a variety of roles, including principal investigator and research contributor, project and program manager, technical group leader, department chief scientist, and leader of several initiatives. Most of his work over the last 15 years is focused on improving the actual operating efficiency of buildings and other energy systems. For 6 years before joining PNNL, Dr. Bromley was a faculty member at Washington State University Engineering School in St. Louis. So, Michael, thank you very much and look forward to your presentation. You able to verify audio and get your presentation up? There we
yes,
go.
can you
Good
hear me,
audio.
Jeff?
Got good audio. You're 5x5.
I'm not seeing that button. I clicked to get full screen though.
It should be in the center of your lower toolbar.
Oh, here we go.
Great.
Let's make sure I click the right window. Yes. Share. Do you see my
Okay.
presentation mode?
We do. We're not in full presentation mode. We're in sort of an edit mode.
That's not what I had displayed.
What you had before worked really well.
Yes, I know. Let's try this one more time. No. Do you have full
No,
display now?
We do not, but you might be able to use that upper button on your ribbon of your PDF file. Well, nope, still didn't work. We're back to just.
All right, hold on. I think I have it solved now.
We're
I
all learning all these.
apologize.
No, we're all learning different platforms, and that's just part of the way life is these days.
How's this?
That's looking great. Go for it.
All right, great.
I'll get off stage.
Well, good afternoon, everyone. I'm Mike Bromley from Pacific Northwest National Laboratory, and I will be presenting some results of work that we've been doing for the Department of Energy on water heater control for demand reduction. The work presented is part of a project for the Department of Energy known as Connected Homes. In this project, we're focusing on developing behind-the-meter control system that will enable existing homes, and that's with common non-connected equipment and appliances, to interact with the power grid to provide service to the grid. Some of the key drivers behind the project overall are we're seeking the lowest possible total cost solution. So that includes installation, not just the first costs. To accomplish this, we do things like automate system setup and configuration. This reduces the time that a installer needs to be in the home. We also minimize the additional number of sensors for the control. And again, same purpose. Our solution accommodates each household's preferences for comfort and convenience. And our control automatically captures the unique characteristics of each home and its appliances. The reason for this is if you capture the characteristics of each home, you squeeze out as much as possible in terms of demand response. And finally, in deployment, we plan to leverage existing platforms so we can spread the cost of the platform over multiple applications. And finally, our solution will be flexible with respect to programs, incentive types, and to some extent, grid services that are provided to the grid. As most of you probably know, electric resistance water heaters represent about 91% of all electric water heaters. We expect that heat pump water heaters will rapidly catch up on this. So our control system structure is shown here. I want to highlight a couple things. There's something in the bottom right called Device Central. This is generally a Raspberry Pi where we run our control algorithm. It accepts a signal from the grid. As you'll see, we will focus on price signal, but we can also have a direct request for a certain amount of demand reduction. We also use a retrofit control device that serves as our interface to the water heater. And by the way, if I didn't mention it, we're focusing on electric resistance water heaters. The one that we're using includes a power measurement, and it's from Shifted Energy. We only use one temperature measurement, the lower temperature, and we found that sufficient for controlling the temperature available to water draws. The method of control we use is Model Predictive Control, or MPC. It's a data-driven approach. It uses optimization, and in this case, we optimize to minimize over a time horizon. Our time horizon is 24 hours, and we used 5-minute control time steps. 24 hours may be longer than we need, but that's what we've been using so far. And the reason we have a time horizon is to account for future water draws. So we can plan how best to use our energy. So we minimize the total price or total cost of energy, price times energy, plus a penalty for lower temperatures than permitted. And those temperatures are established by these conditions that the optimization is subject to. And we determine the amount of energy for that time step based on this optimization. We have upper and lower bounds for energy. We have upper and lower bounds for temperature, which reflects the comfort of the water. And then finally, we only implement the result. Although we do this optimization over 24 hours, we only implement the result for the very next 5-minute time step. Then we do another optimization for the following time step, and so forth and so on. This is our water heater test bed. Diagram on the left, a photo of part of it on the right. There's two things here that are different than the deployment system. We have an additional temperature, the upper temperature, and we have flow control. And if you've run tests on water heaters, you have, I'm sure, controlled the flow, and that's the purpose of the box on the left. I'm going to jump to testing results next. Before doing that, I want to just point out that the results we'll be looking at are for the two 24-hour price profiles here. The upper one is for a time of use rate. The peak period is from 4 p.m. to 11 p.m., a 7-hour peak period. The off-peak price is 8 cents. The on-peak price is just a little bit over 16 cents per kilowatt hour. On the bottom, We have a 5-minute real-time price. We're looking to the future to see how the control will behave for this case. We're using data from ComEd from their 1-hour real-time price program, but they publish data at a 5-minute interval, and that's what we're using here. The red portion of the plot of prices is a 7-hour period that has the most variability in price during the day. So we use the same length of time as the TOU peak rate period, but it shifted a little bit because we wanted to capture this period of greatest price diversity, assuming that it represents conditions on the grid and the time at which response would be most valuable. We use 4 water draw profiles, one based on July, which has the lowest, I believe, annual total water consumption, and for the location considered. We get these profiles or base these profiles on the DOE Building American Water Draw profiles. And we also use November, which represents either the highest consumption or the second highest consumption of the year. Now I want to jump to some results. This is the first set of results and the only set of results I'm going to show the detail that I show here with plots of details. So this corresponds to the TOU electric rate. It uses the November average draw profile, and I've already defined the time period of the peak period, 7 to 11 p.m. or 4 to 11 p.m. We have on the top graph power plotted against time of day. The green line represents the control power limit that comes from our control algorithm. The yellow line represents the actual measured average power during each control time step. So we want the yellow or light brown line to always be below the green line. And as you can see, in most cases, it's satisfied. There are a couple cases where it's not, but they're generally for only one time step. On the bottom graph, we have plot of temperature versus time. The red line represents the upper temperature in the water heater. As you can see, the lowest it gets is slightly above 110 degrees F, probably around 112 degrees F. And it's generally in that range and about 122 degrees F. The blue line represents the lower temperature. You can see that also remains relatively high, except near the very end of the peak period when it drops significantly. And the reason for this is it's trying to squeeze out as much reduction in demand as possible right up to the end of the peak period. And then it's followed by a recovery period. We let it recover immediately, but that could be controlled. Now I want to show you some results for energy impacts and demand reductions. Again, these results are going to be for the TOU price profile. I want to emphasize that the results shown here are simply for implementation of the control that I've identified. It does not include any changes in hot water use behavior, but we're trying to still shift the demand outside of the peak period with the control. So on the left-hand side, we have plot of daily energy use. Dots are shown here for specific draw profile measurements. We label them 1 to 4. They're the profiles I showed earlier, and there's a key to them on the upper right-hand side of the slide. As you can see from this, we have the total daily energy use plotted against total daily water draw, and black represents a baseline for normal operation without our control, and orange represents both data and a fit line for test data. As you can see, there's very little impact of energy on energy, but the impact is in the direction of saving energy relative to the baseline. So there's little energy impact here, but a little bit. On the right-hand side, we have plotted peak period power demand. We have that plotted against water draw during the peak period in gallons. As you can see, for a 10-gallon peak period water draw, we achieve a estimated or measured demand reduction of a little bit over 79%. And out at the 50-gallon peak demand period water draw, we have a savings just a little bit over 34%. Now let's take a look at the results for the real-time price. Looking at energy on the left, I just want to highlight the energy savings. In this case, we get a little bit more significant savings, about 10% at a 40-gallon total daily water draw, and a little over 12% for 140 gallon water draw. The magnitude of the demand or the energy savings is larger at the larger water draw, as you might expect. On the right, same plot as on the previous slide, but with this particular case, at a water draw of 20 gallons during the peak period, we achieve over an 82% demand reduction, and out at 60 gallons during the peak period, we achieve 55% demand reduction. So a little bit more than the time of use case. Other factors that we've investigated are listed here. The first is that the previous results have the actual water draw being identical to the water draw. You might think of it as predicted water draw. And this is to account for actual water draw deviating from day to day somewhat. When we did these tests, we found that the impact on the ability of the controller to provide what we wanted was the difference was very, very small, much smaller than we had expected. Other things we've tested is a 3-price tier TOU. We also have looked at updating the water draw profile. This is the one that's put into the controller once a month, beginning of a month, using the last week of the previous month to learn a new profile.
Mike, I just want to give you a 2-minute warning if I can.
Okay.
Great.
And we're also looking at the price prediction accuracy for real-time prices on the quality control, and this is ongoing. Some deployment-related information. It requires 2 sensors, lower tank temperature sensor and a power sensor. The power sensor could be provided by the retrofit control device that's used as the interface to the water heater. Installation, as you would expect for a water heater, which are generally, not always, but generally 240 volts, requires an electrician, but the installation time should be less than an hour. And we can also share the platform with space heating and cooling, and actually others. And we have a diagram on the right-hand side showing that configuration. And finally, we've estimated the potential installed cost because we don't yet have our final design developed at somewhere in the range of $200 to $500. What's next? We're going to develop a home-ready version. We're going to implement our automated configuration. We're going to explore existing deployment platforms to leverage one of those rather than using our own. We're going to move data processing and storage likely to a cloud server. And we'll have a simple to use home or a mobile user interface. And finally, after that, we'll be looking for collaborators for field testing and demonstration in occupied homes. I'd like to acknowledge my fellow team members who co-authored this presentation. And finally, thank you for your attention and your time.
Great, nice work, Michael.
Thank you.
Just hit your timer just perfectly. So our next 2 presenters are going to be combining into this next section for the next 20 minutes. And these are 2 fellows who work quite closely together. I'm going to introduce Tristan de Fonderville first, and then we'll take a brief break. Tristan will be handing the control of this over to Don after that. Uh, Tristan is the founder and president of Skycentrics, a leader in open standards, smart building solutions that include the CTA 2045 EcoPort, OpenADR, Voltron, and Linux. He has more than 20 years experience in software and hardware, engineering management, including at Apple and SRI. And for those of you who aren't familiar, that's Stanford Research Institute. Tristan is on the Consumer Technology Association Committee, managing the CTA 2045 EcoPort standard. He co-leads the Advanced Water Heating Initiative Subcommittee on Connectivity and Controls, as well as working with NEA, ACEEE, Energy Star, the National Labs, and OpenADR, as well as Voltron and other places. Tristan is one busy dude. I can speak to personal experience with that. He's also very active in the Grid Interactive Building initiatives and is demonstrating savings throughout lowering grid costs, improving grid efficiency, decreasing carbon emissions, and increasing the use of renewables. So Tristan, off to you.
All right, thanks a lot, Jeff. So we will jump into the deck right away. So we're going to be doing this where we talk about the EcoPort certification and qualified product list standard.
It's not quite a full screen, Tristan. Sorry to interrupt.
Thank you. Appreciate it. And Skycentrics makes Wi-Fi and cellular CTA 2045 EcoPort modules, and we help companies get EcoPort certified and OpenADR certified. So here's the new EcoPort label for those of you who haven't seen it yet. Very exciting. Don will be talking about the branding and how that worked. The goal of this presentation is to help everybody get as many products onto the qualified product list, water heaters, obviously, but eventually pool pumps and others. That EcoPort product list, qualified product list, is going to be hosted on the ecoport.openadr.com site. There will also, so it's up here at the top and also down here, there will be information there as well as at Skycentrics on these systems. And we hope, obviously, ecoport.com taken, but we constantly work to try and get an easy link to get to EcoPort by itself. But those are the URLs. So I'm going to be going over the certification process, certification documents, and some white papers are going to be hosted at these areas as well. One on security for the EcoPort, some sample utility programs, and then how OpenADR and EcoPort work together. We're very excited that we're being hosted by the OpenADR Alliance because, as you know, historically, there's been some confusion about OpenADR and CTA 2045. Are they competing? And so we're excited to be hosted at the OpenADR and showing how we're working together. And for those of you who are a little less familiar, the key difference is that the EcoPort is a hardware standard. You must have an EcoPort on your machine and have it be able to respond to certain software commands. The OpenADR is software only. And we believe that it's critical for both long-term future-proofing of connectivity to an appliance to avoid stranded assets, as well as if a manufacturer is going to only choose one way of communicating, typically it's going to be Wi-Fi. As you know, there's some tricky parts about Wi-Fi, so it's important to have other options, and that's what the EcoPort does. You might have cellular, power line carrier, etc. So the certification process, first step is you must be an OpenADR Alliance member. There's a graduated fee structure for that, so smaller companies can get in at less of a cost than the bigger ones. And then you'll be purchasing test tool hardware and software. Basically, OpenADR recommends that you purchase a tool to help you test your own system for OpenADR, and we followed the same process for the EcoPort. The only difference being that the EcoPort has a hardware component, as I mentioned, and there's different hardware for each thing, whether you're a smart grid device, SGD, AC powered or DC powered, and then a universal communication module. Most companies are typically doing only one of those. The module makers are making typically an AC and a DC module. And you require a Windows 10 computer with a USB port. The software is Java-based. It's similar to OpenADR certifying software. And finally, the documents are similar as well. There's a certificate of conformity and a PICS, which is where you describe what kind of conformance standards and specifications your solution, whether it's a module or a water heater, is doing. Then there's a test report that's generated by the software, and that shows that you passed. And there's some config file and notes on the software so that you configure it as you run it. And then we will have you be doing this at UL or Intertek. And ideally, it would be done when you're doing other UL 916 or Energy Star testing, because for the water heaters, they typically need to be plumbed and given electricity and filled with water. That takes time. You might as well do it while you're doing other things. So this is what we ship with the test tool hardware. It's there. I'm not going to go over it. It's a list of documents. I've gone over the main idea, but there's software and hardware. So I did want to spend a little bit of time going over the critical features of CTA 2045-B Level 2. This was the update to the CTA 2045 EcoPort specification that came out in October of last year. So the idea is that the module to the SGD is able to send 64 time price pairs for time of use or dynamic prices. So we wanted to encompass time of use, but at the same time, it's really important. Utilities really want to get to dynamic pricing, at least 24-hour ahead. If you go to our website, you'll notice that I do an animation of the Cal ISO curves for daily demand. I compare the 15th of every month for a year, and I also look at August in 1 year. And you can see that the daily fluctuations between the peaks, the morning and evening peaks, and the valley, and how deep the valley is and where does the valley start, change even every day in the month of August. So we think that it's critical to support more and more renewables, to have a more resilient grid, to be able to do 24-hour ahead dynamic pricing. And as you know, that'll never be in time of use, right? Time of use, you have to have billboards up telling people that you have about 6 months to comply. So the 64 time price pairs means we can send a schedule of time price pairs down to the water heaters. There's been a little bit of pushback there, so we may be modifying that to 24 just to support OEMs getting qualified very quickly. And they're planning on doing that in the next month or two. We should have the qualified product list up. Advanced load up, you've heard it in many other places here, but it allows you, if you have a mixing valve, to go to a higher set point and store more energy. And then there's a get user preference level, which allows the water heater manufacturer to say to the user, to give him an interface. Does he prefer to save money, or does he prefer to spend a little more money and have more guaranteed hot water? And finally, there's an efficiency level control, so utilities can see whether it might be in hybrid mode with the element on or not. If you go to our website, there is a detailed summary available of the differences between the old CTA 2045-A and the new -B, and some color coding so that you can see what's new and what's not. We also like to point out the good citizens of the manufacturers who have been working on this standard for 10 years. They're in green on the left, and that'll show what they've generally been supporting over the years. And I want to make sure I leave enough room for questions and to speak with Don, and for Don's presentation and Don's introduction. So Jeff, I'm going to move it over to you. I think I'm going to be pulled out of the screen, and Jeff, you'll take over.
Great. Thank you, Tristan. I think it's really important for us all to understand that this is quickly changing, but it's getting pretty legitimate. CTA 2045 is a physical standard, but it's also a communication and command structure standard. So there's some fun things, and it's going to allow utilities to integrate renewables in a very simple and straightforward way. So our next speaker is going to be Don Delchinos, and he works at the OpenADR Alliance, and also has been very instrumental in developing the EcoPort branding, logo, and utilization. So Don serves as a director of market facilitation for OpenADR Alliance. And in this capacity, Don seeks to drive awareness and adoption of the OpenADR standards, both across global energy utility markets, as well as expanding array of use cases ranging from distributed energy resources to EV charging infrastructure to the in-home thermostats and ProServer devices. In prior work as a senior vice president of Cable Television Laboratories, Don was an active participant in the NIST and Smart Grid Interoperability Project, now the Smart Grid Power Alliance, the OpenADR Alliance, and the Zigbee Alliance. So this guy is into alliances. Just wish some of our Russian friends were a little bit more aligned with our alliances. And Don has served as the executive director of Entertainment ID Registry, a global media and entertainment meta standard and database. Don also worked at a gas and electric utility as an economist on regulatory and legislative issues at the U.S. and state and federal levels. So Don, you got plenty of time here. We got about 8 minutes, and then we will be wrapping up and moving to a Zoom for questions. Encourage people to keep putting those questions, and I'll be cataloging those and pulling them into the Zoom. So Don, go ahead.
Great, thanks, Jeff. Can you hear me okay?
Bye-bye.
Great. So, and thanks, Tristan, for covering the certification process. So, you know, EcoPort is a name for a brand name for the devices that pass the testing to the CTA 2045 standard. So that's the difference between the brand and the standard name. And this came about partly because the applications of this interface are not limited to just kind of a communications function, but are kind of an active part of having these devices, large appliances, be part of the utility grid and be part of a distributed energy resource network. And so there's a consumer-facing element of this when consumers are looking to tell the utility, can I participate in this program? And so they're going to look for a brand name. And so that's where EcoPort came from. A little bit of the process here, next slide, please, Tristan, is that the brand suggestion actually came from the technical working groups. They were thinking of, and these included utilities on one side, manufacturers on the other. And so the idea was to brand the standard, which is a little bit different than a consumer product. So a little bit more of a constrained process here, not hiring high-end marketing people, but just trying to come with a simple name that would explain what this thing is. We did check with CTA itself, also AHRI and the state agencies that have been part of the development here, just to make sure they didn't want to lead that branding effort, and they were happy to delegate it back to the certification working group. So that's us. But the broad nature of the stakeholders was important. So you've got utilities involved, have been involved in the technical part of this. So their demand management folks were part of the spec process, but also program developers, people who run demand response programs and try to sign up customers, utility customers to participate. That's the kind of expertise we needed in this group. Also including then the manufacturers themselves, of course, starting with water heater folks, but also a lot of those companies also have other lines of business, and so pool pumps and other things that are going to come in later. And finally, the state regulators themselves, and so they were all part of this this process. So next slide, there's a little more detail on that. Tristan, if you hit the next one. Oops, there you go. So this is just a little detail on who those participants were. So a good cross-section of utilities geographically across the country, a good cross-section of the manufacturers themselves, and then, as we say, some other kind of stakeholders, regulatory and advocacy groups were also consulted. Next slide, please. And so, long story short, and it was a couple of month process. We didn't want this to last too long, but enough to get all the ideas on the table. And so EcoPort became the name that was selected for these certified products. We then turned around and hired a graphic designer to come up with some designs here. And so you see, this is actually a subset of a longer list of kind of styles that could be used. And maybe the colors, EcoPort was meant to evoke, ecological, environmental value, but also economic value. And so it's kind of could be interpreted both ways. And so consequently, we had a couple of different color schemes, green for the environmental side, but also blue as a more sort of smart energy, kind of future facing graphic. So there's a lot more detail on the graphic elements to this and what they connote, but we'll save that for another time. Next slide, then the next two slides, go ahead and move past this. Our designer also put together a pretty detailed style guide, which includes not only what these things look like and how they should be used, but also a little bit of the history and the mission of kind of underpinning what it is. And so that is, and the next slide. So that slide is that graphic is available online, and come back to that. So again, the brand may only be used for the certified product. The technical standard itself is an open standard. Anybody could see that and build to it, but the brand can be used only with the certified product, as Tristan laid out. The brand is right now a certification mark and has been submitted for formal trademark registration, and that happened back in September. And the attorneys felt it was fine to continue with the commercial work, and so there are companies testing and in the pipeline to be certified, and they can use this mark when we get to that point. The trademark office itself, as maybe a lot of government agencies are these days, taking a little longer than they used to. So we're still hoping to hear the formal response. So in the meantime, the proper usage is to just have the logo itself or use the CM for certification mark. And then when the registration is complete, to use that R, which is widely recognized. So the style guide is published on our website, the Alliance website. And then there's camera ready art that goes with this that the manufacturers want to use on the products themselves. And that's available, again, upon certification. So next steps, for more information on all of this, in addition to what Tristan showed, you can go to currently openadr.org/ecoport. That's a provisional site until we get the final domain name registered, which is in process now. You mentioned a white paper earlier to communicate better to especially the utility program managers how to engage with this brand. We'll finalize the trademark. And then my branding work is done, and what I'll be still involved in is outreach to especially the utility audience. And so we have a panel coming up in the first week of April at the Peak Load Management Association. This is utility professionals who run demand response programs. Rolf Bienert will be on a panel there with a gentleman from Portland General who will kind of handle the utility side of that. We'll also be there at Distributech with an exhibit of both OpenADR and EcoPort, so hopefully reach a large utility audience there. And as I said earlier, there's a broader range of utilities that are interested in this, not just in California, Washington, Oregon, but much more broadly. So final slide is sort of the marketing piece. And again, there's a lot of benefits to this, not only for the grid efficiency, but for a lot of other good goals around carbon reduction and building jobs and equity, and essentially a more resilient grid. So with that, I think I've got my contact on the next slide. And, or maybe I don't, but that's all I've got, Jeff. So back to you.
Great, thanks, Don. Nice way of understanding how this brand and mark are going to work, and Tristan on explaining how a product can get certified and listed. So I think at this point we're going to move to the Zoom room, and I'm going to ask our ACEEE person to put that contact info or that Zoom link into the notes section. And if you can't see it there, it should be in the initial invite that was given to you to subscribe to this session. So we'll all migrate over there. Give us probably a minute to kind of organize and get ourselves situated, and then we'll get into some of the questions that have come in over the webinar. Thank you so much, everybody, for participating, We look forward to seeing you in the Zoom room. Bye-bye now.